Welcome back. So in this video, we are going to study what is the capacity of the channel when the transmitter and the receiver both have the channel side information, and now we would also carry out the power control. So the system looks like this. So at the transmitter end, we have this box as the entire encoder or the system encoder. At the receiver end, you have a system decoder. But now, assuming that the channel can take capital N states, instead of one encoder as was there in the fixed rate encoding, there can be capital N encoders here. And then depending upon what the estimate of the current state is, one of the encoders would be hooked onto the transmitting side. And in addition to that, there would be some power control that would be carried out. So this X sub I would be a variable rate, variable power signal that would get transmitted into the channel root G sub I. White Gaussian noise would be added into the system, and then at the receiver end, there would be a demultiplexer that would connect the receive signal to the relevant decoder that is required to decode this information depending upon again what is the current estimate of the channel. So, that's how the system model works. So you can have you have n encoders at the transmitter side, you have n decoders at the receiving side, and in order to carry out the power control, what would happen is we would define gamma j. Suppose gamma j is our current state, and we can carry out the power control as well. So suppose Pj is the transmitted signal's power when the channel is in the state gamma j. Then the received signal to noise ratio in that case would be equals to Pj times Gj, which is the power gain of the channel, divided by N naught P. So that would be what? That would be your signal to noise ratio when the channel is in the jth state. However, we would tweak this a little, as has been done by the author of the textbook. We would define another variable gamma to be equals to P bar times Gj over N naught B, where gamma, you can see, is the instantaneous signal to noise ratio when P bar is transmitted always. When P bar is transmitted, the channel state, which would still depend on what is the current channel state, because Gj is your channel gain at the jth state, divided by N naught B. The reason for doing that is that now if we have defined gamma in this fashion, you can rewrite gamma j to be equals to Pj times gamma over P bar. So in a way, you are normalizing the current power, which is you are transmitting for the current state J, by the average power that you are allowed to transmit times gamma, which is related to the current state of the channel. So that is how we would define gamma j, and that would be equals to Pj gamma over P bar. So that is gamma j for you. And now under this condition, what would be the total probability, what would be the total capacity of the channel? So now we can define the capacity C to be equals to summation j equals 1 to n b log base 2 of 1 plus the signal to noise ratio. But now the signal to noise ratio would be equals to Pj gamma over P bar And this, all of this has to be multiplied with the probability that the system is in the jth state. Let me call that probability as pj tilde. So pj tilde is what? Pj tilde is the probability that the system is in state j, or in other words, your gamma j, your instantaneous signal to noise ratio is equals to gamma j. So, but that is your capacity. That is your capacity, but that can still be maximized. Why? Because this power, you can control that power. So what would be the maximum capacity? What would be the optimal capacity under these conditions? So the maximum capacity C, the capacity C, which is the maximum capacity, would be equals to, it would maximize over the power that you can transmit, your capacity summation j equals 1 to n b log base 2 of 1 plus the signal to noise ratio, which you have defined like this, times the probability that you are in the jth state. That is the maximum capacity, and that maximum capacity, you cannot transmit it unlimited amount of power. You must have a power constraint, a total average power constraint. So subject to summation j equals 1 to capital N, Pj times Pj tilde is equals to, is less than or equals to P bar. So that must be your total average power constraint. So Pj is the power you're transmitting when you are in the J state. Pj tilde is the probability that you are in the J state. You take the product sum for all values of J from 1 to N. That must be less than or equals to some threshold that we are calling P bar. And of course, Pj must be greater than or equals to 0. You cannot have a negative power. So that is your capacity. That is the maximum capacity that you must have, that you can convert. So that you would have if you are also carrying out the power control. So this is the discrete time version um, of the capacity. The continuous time version is very similar. You would have an integral instead of this. So if so, C would be equals to max. You would maximize over P of gamma, where gamma P of gamma would be the power that you're transmitting when the channel is the state gamma. Integral from 0 to infinity b log base 2 of 1 plus P of gamma over P bar times P gamma of gamma d gamma, and again that must be subject to some average power constraint. So that is the continuous time version. So we can solve either of the two, but we would solve the discrete time version, although the complexity difficulty level is the same for both. So let's try to find out how can we compute that. So you can see that this is an optimization problem, and optimization problems can have lots of types, but this is not a very complex optimization problem. So you can have convex optimization problems, you can have non-convex optimization problems, you can have concave optimization problems. But broadly speaking, you can categorize your optimization problems as either convex or non-convex optimization problems. The convex optimization problems have have a special characteristics that their local minima would give you a global minima. So every local minima for a convex optimization problem would be a global minima. So it's easier for a convex, if your objective function is a convex function, it's easier to compute the optimal point. So this under the convex, you can have convex as well as concave problems, because if you have a concave function, like for example, a log is a concave function, all you need to do is to multiply that with a negative sign. That would make it a convex problem. And the pro and the property of the convex optimization problem is that it must have its constraints, the objective function, and the constraints, all of them should be convex and or linear. So your objective function as well as the constraints um, must either be convex functions or they must be linear functions. So suppose you have a function f of x and you want to solve it. Suppose if this is your function f of x, so you can see that this is a convex function. It has only one global minima, and as you would uh, you can solve this problem by different methods. There are different solvers available, uh, and most of the solvers, what they would do, they would start from a point, they would compute the gradient, and they would move in the direction of the negative of the gradient, and in the hope that they reach an optimal point where the slope of the functions would be equals to zero. There would be only one point in the entire function if it's a convex function where the slope is exactly equals to zero. Uh, so that is how you can solve, you can find the minimal point or the minima in a convex function. Similarly, you can have a concave function. If the function is concave, it would have only one maximum point. So if this is a f of x, it would be a concave function. So typically in the standard form, what you would do that you would write the optimization problem in a standard form. In the standard form, you would write the optimization problem in this fashion. So for example, f naught of x is the function that you want to minimize, and if you have a concave function, you would convert into a convex function. So in the standard form of the optimization problem, this f naught of x is always assumed to be a convex function. So in other words, you would be minimizing this function f naught of x subject to some constraints which can be inequality constraints, and then there can be some constraints which are, sorry, equality constraints. So this is equals to zero. So these functions where I can vary from 1 to n, must be either convex or linear. So this is the standard form of a convex optimization problem. So you would have a convex function, you would write it minimize over x, f naught of x, subject to your inequality constraints, and then there can be some equality constraints. So if you take an example of a log function, the log is a concave function, and if you want to find out whether or not the function is convex or concave, you have the second derivative rule. For example, you have this function log of a plus bx. Remember, log is a concave function, which it takes the positive values of the argument. Thus, a plus bx in total must be a positive quantity for all values of x. So if this is your log function, and then you would take the derivative of this with respect to x, so that would be equals to 1 over a plus bx, for example. And then if you want to take the second derivative of this function, that would be equals to minus times a plus bx whole to the power minus 2. You can see that this is a positive number. 1 over a positive number square would still be a positive number. Hence, what you get is a negative number. So this is a negative number, and hence you can see that this is a concave function. So this is a second derivative rule that allows you to find out whether or not your function is a convex function or a concave function. So because this is a concave function, you can very easily convert that into a convex function by writing a minus f of x. So minus f of x would be a convex function if f of x is a concave function. So now let's get back to the problem that we are going to solve. And there, as I've said, there can be multiple methods to solve that. So we would restrict ourselves to the method that the author of the textbook has used, and she has used the primer dual formulation to solve this problem. That is also called the method of Lagrange multipliers. So it's not very difficult for this basic set of optimization. So let's try to do that. So remember, what we are trying to do is we are trying to find out what is the capacity of what is the maximum capacity when both the transmitter and the receiver side have the channel side information, and the expression we needed to maximize was this b log base 2 of 1 plus pj gamma over p bar times pj tilde. So this you need to maximize subject to a few constraints, but there was summation j equals 1 to capital N. But what we would do, we would put a minus sign here, and we would minimize this function over what? Over pj, where pj is your power control, and subject to summation j equals 1 to n, pj tilde is less than or equals to p bar, and you assume that pj is greater than or equals to 0. So that is your problem in hand that we want to minimize. So we'll stop here. We'll solve this problem in the next video.